What if the very walls of our buildings could breathe in toxic air and destroy pollution? No heavy machinery, no active electricity, just a simple coat of paint. Right now, our cities are suffocating under a blanket of vehicular emissions and industrial nitrogen oxides. But using a blend of material physics and quantum chemistry, we've formulated a passive, solar-powered air purifier. Here is the exact chemistry that makes it happen. The secret ingredient is an ultrafine, pure anatase titanium dioxide nanopowder. In material physics, there are two polymers of titanium dioxide, rutile and anatase, and the major difference in these forms are their crystal structure arrangement, that completely changes how they interact with the light. Anatase form is less dense and has more open tetragonal structure, which makes it less stable, hence its surface atoms are more active. Anatase is a semiconductor with a wide optical band gap of 3.2 electron volts. When ultraviolet, UV, light hits an anatase crystal, it excites electrons and creates powerful, electron-hole pairs.
These pairs react with moisture and oxygen in the air to create highly reactive oxygen species, like hydroxyl radicals, that aggressively break down organic pollutants, dirt, and nitric oxide gases. Now you may be wondering, what are the electron-hole pair? To understand that, we have to look at the quantum behavior of electrons in a solid material, like this titanium dioxide catalyst. In a semiconductor, electrons aren't completely free to roam, nor are they entirely locked in place. Instead, their energy options are divided into two distinct energy bands: the valence band, the lower energy level where electrons normally sit, bonded tightly to the atoms. The conduction band, the higher energy level where electrons are free to move and conduct electricity. Separating these two bands is an empty energy gap called the band gap. How an electron-hole pair formulates: normally, the valence band is completely full of electrons, and the conduction band is empty. But when a photon of light carrying enough energy, like UV light hitting your anatase titanium dioxide, strikes the material, an elegant chain reaction occurs. The excitation: an electron in the valence band absorbs the incoming light energy. If the energy is greater than the band gap 3.2 electron volts for anatase, the electron gets kicked up across the gap into the high-energy conduction band. The electron, this newly freed electron, is now a negatively charged mobile carrier, ready to participate in chemical reduction reactions. The hole, because the electron left its original spot in the valence band, it leaves behind an empty space, or a vacancy. In physics, this missing electron behaves exactly like a positively charged mobile particle, which we call a hole. Together, this liberated, negatively charged electron and its corresponding, positively charged vacant spot are called an electron-hole pair. This figure shows the follow-up reaction. The hole left behind in the valence band is incredibly unstable, it desperately wants an electron to fill its vacancy. Because of this, it acts as a powerful oxidizing agent. When humidity or moisture from the air touches the paint surface, the hole steals an electron from the water molecule, turning it into a highly reactive hydroxyl radical. Meanwhile, the free electron in the conduction band acts as a reducing agent. It quickly attaches to oxygen molecules floating in the air, transforming them into superoxide radicals. These two radicals act like molecular scissors. When toxic car exhaust fumes like nitrogen oxides hit the wall, these radicals attack the pollutant molecules, breaking them down into harmless traces of nitrate that sit quietly on the wall until the next rain washes them away. This whole light activation process is known as photocatalysis.